The final topic we'll be talking about in terms of origins of quantum mechanics and experimental data that can't be explained is the hydrogen atomic spectrum. And so this one's near and dear to my heart as a spectroscopist. And we notice there's a theme here. A lot of these things involve light. And that's really still the way we learn a lot of what we know about quantum mechanics is via interactions between light and matter, or spectroscopy. And so many of the experiments we're going to be doing in this class revolve around this idea of measuring absorption or emission of light from atoms and molecules. And so what we're looking at here is what we can do is we can place hydrogen atoms in a glass tube and then send electrons through the tube. This is a really crude drawing. It's actually, more complicated than this. But we send an electrical current through the tube, and that will excite the hydrogen atoms, and they will emit light at a specific color. So this is similar to, say, how a neon light works. We have neon and other types of gases inside of those lights. We send an electric current through them. It excites the atoms inside of the gas, and they emit light at specific colors. And so one thing that's interesting about the hydrogen atomic spectrum is that, unlike a black body where we see, we saw those curves where we get a nice, kind of bell-shaped curve as a function of wavelength, a hydrogen atomic spectrum, if we plot, the intensity of light versus wavelength, we see instead of a big curve like this, we see several individual lines. So this is what we call a line spectrum. Hydrogen only emits light at very specific frequencies. And so this was observed in the 1800s, but there wasn't a lot of explanation as to why it occurred this way. Hydrogen had a very, characteristic, and it was obvious that there was some sort of pattern present, but it wasn't clear what the pattern was or how to explain it. And so this is, if we look at sort of a figure showing, this is a representation of that. So we see, there is different sets of lines that we understand now why these different lines occur, but we have the Lyman series in the ultraviolet, the Balmer series in the visible light series, and then into the infrared we get the Paschen series. These are named after different people who observe these lines and then kind of work to explain them. And so the first set of lines that were explained was this visible lines, the set of visible lines, the Balmer series. And Balmer was I believe a school teacher, wasn't necessarily a specifically trained physicist, who got interested in this and figured out that if you plot the frequency of light versus an integer, again, integers show up again, versus 1 over n squared, n being 3, 4, 5, etc., you get a linear plot. So there's, again, some sort of relationship here that depends on specific amounts, right? Integers. The fact that these integers are showing up is a clue, again, that there's something quantum going on here. Only specific integers are allowed. And so this can be, we can write this equation out as the frequency is equal to a constant, right? So this is the slope, 8.2202 times 10 to the 14th hertz, times 1 minus 4 over n squared. And again, in this is specifically for the Balmer series, n is 3, 4, 5, etc. And so when we talk about hydrogen spectra, we often convert this to different units. So as a spectroscopist, one of the common units we use is what's known as wave numbers, centimeters to the -1. And this is 1 over wavelength, where the wavelength is in centimeters. And so this ends up being a more useful, an easier unit to use. And so we can rewrite this equation as the wave number. So we write the wave number as nu tilde, with a tilde over the top, is equal to 109,680 wave numbers times 1 over 2 squared minus 1 over n squared. Again, where n starts at 3. So we can actually, it was discovered eventually that we can explain the entire spectrum with an equation that looks like this. So the Balmer series is specifically where we have n equals 2. We'll call this nf. And ni is equal to 3, 4, 5. But if we vary both of these integers, we can explain all of the spectra. So the general equation, what's known as the Rydberg formula, is that the wave number is equal to the same constant that Balmer found, 109,680 wave numbers. This is known as RH, the Rydberg constant, times 1 over n1 squared minus 1 over n2 squared, where n2 will be bigger than n1. So for the Balmer series, n1 is specifically 2. And if we go back up to our plot of all the different series, we see we have different n values here. So the Lyman series in the ultraviolet, n2 is equal to 1. For the Balmer series, n2 is equal to 2. For the Paschen series, n2 is equal to 3. And there you can continue on, right? And we also see this relationship where as the other n value, right, n1, as it increases, the lines get closer and closer together, and we end up with a specific, sort of limiting behavior here. And so the sense that we get here again is that we have integers showing up, which means we have quantum behavior. And so this was yet another evidence that this quantum thing that Planck thought of as just a mathematical necessity to fit the data and would be explained away at some point was in fact real. This is a physical phenomenon that's showing up in multiple different places. And we'll see eventually that this Rydberg constant is yet again related to Planck's constant. But we need to talk more about hydrogen atoms to make sense of how that eventually shows up.